Hello and welcome to our astronomy course. Today we have lecture number 10. The topic of lecture is the origin of the solar system. Generally, it will be continued the previous topic. Now you have learned enough to put all the pieces of the puzzle together and explain the distinguished characteristics of the solar system in the next table. The disk shape of the solar system is inherited from the motion of the material in the solar nebula. The sun and planets and moon mostly revolve and rotate in the same direction because they form from the same rotating gas cloud. The orbits of the planets lie in the same plane because the rotating solar nebula collapsed into a disk, and the planets form in that disk. The solar nebula theory is evolutionary in that it calls on continuing processes to gradually build the planet. To explain the odd rotations of the Venus and Uranus, however, you may need to consider catastrophic events. Uranus rotates on its side. This might have been caused by an off-center collision with a massive planetesimal when the planet was nearly formed. Two hypotheses have been proposed to explain the backward rotation of Venus. Theoretical models suggest that the sun can produce tides in the thick atmosphere of Venus that could have eventually reversed the planet's rotation, an evolutionary hypothesis. It is also possible that the rotation of the Venus was altered by an off-center impact late in the planet's formation, and that is catastrophic hypothesis. Both may be true. The second item in this table, the division of the planets into terrestrial and Jovian forms, can be understood through the through the condensation sequence. Terrestrial planets form in the inner part of the solar nebula, where the temperature was high, and only compounds such as the metals and silicates could condense to form solid particles that produce the small, dense terrestrial planets. In contrast, the Jovian planets form in the outer solar nebula, where the lower temperature allowed the gas to form large amounts of ices, perhaps 3 times more ices than silicate. That allowed the Jovian planets to grow rapidly and became massive, low-density worlds. Also, Jupiter and Saturn are also so massive they were able to grow by dropping in cool gas directly from the solar nebula. The terrestrial planets could not do this because they never became massive enough. The heat of formation or the energy released by infalling matter was tremendous for these massive planets. Jupiter must have grown hot enough to glow with a luminosity of about 1% that of the present sun. Also, it never got hot enough to generate nuclear energy as a star would. Nevertheless, Jupiter is still hot inside. In fact, both Jupiter and Saturn radiate more heat than they absorb from the sun, so they are evidently still cooling. A glance of the solar system suggests that you should expect to find a planet between Mars and Jupiter at the present location of the asteroid belt. Mathematical models indicate that the reason asteroids are there rather than a planet is that Jupiter grew into such a massive body that it was able to gravitationally disturb the motion of nearby planets in Mars. A body that could have formed a planet just inward from Jupiter's orbit collided at high speed and shattered rather than combining, or were thrown into the sun, or maybe ejected from the solar system. The asteroids seen today are the last remains of those rocky planets in Mars. The comets, in contrast, are evidently the last of the icy planets in Mars. Some may have formed in the outer solar nebula beyond Neptune and Pluto, but many probably formed among the Jovian planets where ices could condense easily. Mathematical models show that the massive Jovian planets could have ejected some of these icy planets in Mars into the far outer solar system. In later lectures, you will see evidence that some comets are icy bodies coming from those distant locations, falling back into the inner solar system. The icy Kuiper belt object appeared to be ancient planetesimals that formed in the outer solar system, but were never incorporated into a planet. They orbit slowly far from the light and warmth of the sun, and except for the occasional collisions, have not changed much since the solar system was young. The gravitational influence of the planet deflects some Kuiper belt objects into the inner solar system, where they also are seen as comets. The large satellite system of the Jovian force may contain two kinds of moons. Some moons may have formed in orbit around planets in a miniature version of the solar nebula. Some of the smaller moons, in contrast, may be captured planetesimals, asteroids, and comets. The large masses of the Jovian planets would have made it easier for them to capture satellites. Notice in this table that all four Jovian forts have ring systems. You can understand this by considering the large mass of these worlds and their remote location in the solar system. A large mass makes it easier for a planet to hold into orbiting ring particles. And being farther from the sun, the ring particles are not as quickly swept away by the pressure of sunlight and the solar wind. It is hardly surprising then that the terrestrial planets, low-mass worlds located near the sun, and have no planetary rings. The last entry in this table is the common ages of solar system bodies, and the solar nebula theory has no difficulty explaining that characteristic. If the theory is correct, then the planets all form at the same time as the sun and should have roughly the same age. For internal processes would have gradually destroyed the solar nebula, aside from the possible external influences mentioned earlier. The most important of these internal processes was radiation pressure. When the sun became a luminous object, light streaming from its photosphere pushed against the particles of the solar nebula. Large bits of matter, like planetesimals and planets, were not affected, but low mass specks of dust and individual atoms and molecules would have been pushed outward and eventually driven from the system. The second effect they helped clear the nebula was the solar wind and the flow of the ionized hydrogen and, and other atoms away from the sun's upper atmosphere. This flow is a steady breeze that rushes past Earth at about 400 kilometers per second. Young stars are observed to have even stronger winds than stars of the sun's age, and also irregular fluctuations in luminosity, which can accelerate the wind. The strong surging wind from the young sun may have helped push dust and gas out of the nebula. The third effect that helped clear the nebula was the sweeping up of the space debris by the planet. All solid surfaces in the solar system is heavily created by meteorite impact. Look at this slide, please. Earth's moon, Mercury, Venus, Mars, and most of the moons in the solar system are covered with craters. A few of these craters have been formed recently by the steady rain of the meteorite that falls on all of the planets in the solar system. But most of the craters appear to have been formed before roughly 4 billion years ago in what is called the heavy bombardment, as the last of the debris in the solar nebula were swept up by the planet. The fourth effect was the ejection of material from the solar system by close encounters with the planets. If a small object, such as a planet's mouth, passes close to a planet, the small object path is affected by the planet's gravity field. In some cases, the small object can gain energy from the planet's motion and be thrown out of the solar system. Ejection is most probable in encounters with the massive planets, and so the Jovian planets were probably very efficient at ejecting the icy planetary mouths that form in their region of the nebula. Attacked by the radiation and the gravity of nebula stars, and wrecked by the internal processes, the solar nebula could not survive very long. Once the gas and dust were gone, and most of the planet's mouths were swept up, the planets could no longer gain significant mass, and the era of the planet building ended. Why are there two kinds of planets in our solar system? This is an opportunity for you to build an argument that closely analyzes the solar nebula theory. Planets being forming from solid bits of matter, not from gas. Consequently, the kind of planet that forms at a given distance from the sun depends on the kind of substances that can condense out of the gas, there to form solid particles. In the inner parts of the solar nebula, the temperature was so high that most of the gas could not condense to form solids. Only metals and silicates could form solid grains, and the innermost planets grew from this dense material. Much of the mass of the solar nebula grew from these materials and consist of hydrogen, helium, water vapor, and other gases. And they were present in the inner solar nebula, but couldn't form, namely solid grains. The small terrestrial planets could grow only from the solids in their zone, not from the gases, so the terrestrial planets are small and dense. In the outer solar nebula, the composition of the gas was the same, but it was cold enough for water vapor and other simple molecules containing hydrogen to condense to form ice grains. Because hydrogen was so abundant, there was lots of ice available. The outer planets grew from the large amount of ice combined with small amounts of metal and silicates. Eventually, the outer planets grew massive enough that they could beam to capture gas directly from the nebula, and they become the hydrogen and helium-rich Jovian core. The condensation sequence, combined with the solar nebula theory, gives you a way to understand the difference between the terrestrial and Jovian planets. Now expand your argument. Why do some astronomers argue that the formation of the Jovian planets is a problem that needs further explanation? And there are other planetary systems. The evidence says yes. Do those systems contain planets like Earth? The evidence so far is incomplete. Visible, infrared, and radio wavelength observations detect dense disks of gas orbiting young stars. For example, at least 50% of the stars in the Orion star-forming region are surrounded by dense disks of gas and dust. A young star is detected at the center of the most disks, and observation allows astronomers to measure the masses of the disks. They contain many Earth masses of material in a region a few times larger in diameter than our solar system. Evidently, disks of gas and dust that could form into planets are a common feature around the newborn star. The Hubble Space Telescope can detect dense disks of gas and dust around young stars in a slightly different way. The disks show up in a silhouette against the nebula that surround the newborn star. Some of these disks seem to focus the gas flowing away from a young star into the two jets shooting in opposite directions. In addition to these dense hot planet-forming disks around young stars, infrared astronomers have found cold, low-density dust disks around all the stars, old enough to be finished forming planets. These tenuous dust disks are sometimes called debris disks because they are evidently made of dusty debris produced in collision among small bodies, such as comets, asteroids, and Kuiper belt objects, rather than dust left over from an original protostellar disk. That conclusion is based on calculations showing that the absorbed dust would be removed by radiation pressure in a much shorter time than the ages of those stars, meaning the dust there now must have been created relatively recent. The presence of dust with short lifetimes around all stars assures you that small bodies such as asteroids and comets must be present as sources of the dust. If those small objects are there, then it is likely that there are also planets orbiting those stars. Our own solar system contains such second-generation dust produced by asteroids and comet collisions. Furthermore, astronomers find that the solar system Kuiper belt, extending beyond the orbit of Neptune, has the characteristics expected of an old debris. Some examples of debris disks are around the stars Beta Pictoris, HD 107, 146, and Epsilon Eridani. Let's look at this slightly. The dust disk around the Beta Pictoris, a star more massive and luminous than the Sun, is about 20 times the diameter of our solar system. The dust disk around Epsilon Eridani, a star somewhat smaller than the Sun, is similar in size to the solar system's Kuiper belt. Like most of the other known low-density disks, both of these examples have central zones with even lower density. Those inner regions may be places where planets have finished forming and swept up most of the construction material. Infrared observations reveal that the star Vega, easily visible in the northern hemisphere summer sky, also has a debris disk, and detailed studies show that much of the dust in the disk is tiny. The pressure of the light from the Vega should blow away small dust particles quickly, so astronomers conclude that the dust being absorbed now must have been produced by a big event like the collision of two large planets in Earth with the last million years. Fragments from that collision are still smashing into each other now, and then and producing more dust, continuing to enhance the debris disk. This effect has also been found in the disk around HIP 8920 and several other stars. Such smash-ups probably happen rarely in a dust disk, but when they happen, they make the disk very easy to detect. Okay, the difference between the two kinds of planet-related disks that astronomers have found: the dense disk of gas and dust seen around newborn stars are sites where planets could be forming right now. The low-density debris disks around some older stars are produced by dust from collision among comets, asteroids, and Kuiper belt objects. Such disks are evidence that planetary systems have already formed there. A planet orbiting another star is called an extrasolar planet. Such a planet would be quite faint and difficult to see so close to the glare of its star. But there are ways to find this planet. To understand how you have to do it is imagine walking it off. You will remember that Earth and the Moon orbit around the common center of mass. When a planet orbits a star, the star moves very slightly as it orbits the center of mass of the planet's star system. Think of someone walking a poorly trained dog on a leash. The dog runs around the pulling of the leash, and even if it were an invisible dog, you could plot its path by watching how its owner was jerked back and forth. Astronomers can detect a planet orbiting another star by watching how the star moves as the planet moves. The first planet detected this way around the Sun-like star was discovered in 1995. It orbits the star 51 Pegasus. As the planet circles the star wobbles slightly, and that very small motion of the star is detectable by Doppler shifts in the star's spectrum. From the motion of the star and estimates of the star mass, astronomers can deduce that the planet has at least half the mass of Jupiter and orbits only 0.05 astronomical units from the star. Half of the mass of Jupiter amounts to 160 Earth masses. So this is a large planet. No, also that it orbits very close to its star, much closer than Mercury orbits around our Sun. Astronomers were not surprised by the announcement that a planet orbited 51 Pegasi. For years, they had assumed that many stars had planets. Nevertheless, astronomers greeted the discovery with typical skepticism. That skepticism led to careful tests of the data and further observations that confirmed the discovery. In fact, more than 300 planets have been discovered in this way, including at least 3 planets orbiting the star Upsilon Andromeda and 5 orbiting 55 concrete true planetary systems. Over 25 such multiple planet systems have been found. Another way to search for planets is to look for changes in the brightness of the star when, from the Earth's point of view, the orbiting planet crosses in front of the star, called a transit. The decrease in light during a planet transit is very small, but it is detectable, and astronomers have used this technique to find several planets. By measuring the amount of light loss, astronomers can tell that all of these planets have Jovian sizes. The Spritzer Infrared Space Telescope has detected infrared radiation from the 2 large hot planets already known from star-wobble Doppler shift. As these planets orbit their parent stars, the amount of infrared radiation from each system varies. When the planets pass behind their parent stars, the total infrared brightness of the systems noticeably decreases. These instruments confirm the existence of the planets and indicate their temperatures and sizes. The planets discovered so far tend to be massive and have short orbital periods because lower mass planets or longer period planets are harder to detect. Low mass planets don't tug on their stars very much, and present-day spectrographs can detect the very small velocity changes that these gentle tugs produce. Planets with longer periods are harder to detect because astronomers have not been making high-precision observations for a long enough time. For example, Jupiter takes 11 years for cycle the Sun once, so it will take years for astronomers to see the longer period wobbles produced by planets lying farther from their stars. You should not be surprised that the first planets discovered the massive and have short orbital periods. What does it mean to be skeptical, yet also opens a new idea? Scientists are just a bunch of skeptics who don't believe in anything. That is a common misconception among people who don't understand the methods and goals of science. Yes, scientists are skeptical about new ideas and discoveries, but they do hold strong beliefs about how nature works. Scientists are skeptical, not because they want to discover everything, but because they are searching for the truth and won't be sure that a new description of nature is reliable before it is accepted. Another common misconception is that scientists automatically accept the work of other scientists. On the contrary, scientists skeptically question every aspect of new discovery. They may wonder if another scientist's instruments were properly adjusted, or whether the scientist's mathematical models are correct. Other scientists will want to repeat the work themselves using their own instruments to see if they can obtain the same result. Every observation is tested. Every discovery is confirmed. Only an idea that survives many of these tests begin to be accepted as a scientific truth. Scientists are prepared for this kind of treatment at the hands of other scientists. In fact, they expect it. Among scientists, it is not bad manners to say, really, how do you know that? Or why do you think that? Or show me that evidence. And it is not just new or surprising claims that are subject to such scrutiny. Even though astronomers have long expected to discover planets orbiting other stars, When a planet was finally discovered cycling 51 Pegasi, astronomers got skeptical. This was not because they thought the observations were necessarily flawed, but because that is how scientists work. The goal of science is to tell stories about nature. Some people use the phrase telling a story to describe someone who is telling a tale. But the stories that scientists tell are exactly the opposite, because you could call them antitheses, because they are as true as scientists can make them. Skepticism eliminates stories with logical errors, flavored observations, or misunderstood evidence, and eventually leaves only the stories that best describe skepticism. Is not a refusal to call beliefs. Rather, it is a way for the scientists to find it and keep those natural principles that are worthy of belief. The new planets may seem odd for another reason. In our own solar system, the large planets form farther from the sun, where the solar nebula was colder and ices could contact. How could big planets form so near the star? Theoretical calculations indicate that planets forming in an especially dense disk of matter would spiral inward as they sweep up gas and planets amount. That means it is possible for a few planets to become the massive, short-period objects and that are detected most easily. Photographing a planet orbiting another star is about as easy as photographing a bug groveling on the bow of a such light miles away. Planets are small indeed and get lost in the glare of the stars they orbit. Nevertheless, a few objects have been detected that appear to be planets, and searches for more are being conducted. For example, NASA's Kepler mission will monitor the brightness of 100,000 stars for 4 years, searching for transits of Earth-sized planets. Other space observations will be able eventually to image Jovian and terrestrial planets around Sun-like stars. The discovery of extrasolar planets gives astronomers added confidence in the solar nebula system. And so about the solar nebula theory. The theory predicts that planets are common, and astronomers are finding them orbiting many stars. Why are debris this evidence that planets have already formed? Sometimes a good scientific argument combines evidence, theory, and an astronomer's past experience, a kind of scientific common sense. Certainly, the cold debris disks see around stars like Vega are not places where the planets are formed. They are not dense enough or young enough to be planet construction zones. Rather, the debris disks must be old, and their dust is being produced by collision among comets, asteroids, and Kuiper belt objects. Small dust particles would be blown away or destroyed relatively quickly. So the fact that we see the dust now means this collision must be a continuing process. Astronomers have reason to expect that where you find comets, asteroids, and Kuiper belt objects, you should also find planets, so the dust disks seem to be evidence that planets have already formed in such systems. Now build a new argument. What direct evidence can you cite that planets orbit other stars? The solar system is this shape, including the orbital revolution of the planets and their moons, and the rotation of the planets on their axis. planets are divided into two groups. The inner four planets are terrestrial planets, small, rocky, dense, Earth-like worlds. The next four outward the Jupiter-like Jovian planets that are large and love dense. All four of the Jovian worlds have ring systems and large families of moons. The terrestrial planets have no rings and few moons. Most of the small, irregular rocky bodies, called asteroids, are located between the orbit of Mars and Jupiter. Comets are icy bodies, some of which pass through the inner solar system on long elliptical orbits. As the ice is vaporized and releases dust, the comet develops a tail that points approximately away from the sun. Meteoroids that fall into Earth's atmosphere are vaporized by friction and are visible as streaks of light called meteors. Larger and stronger meteoroids may survive to reach the ground where they are called meteorites. The Kuiper belt is composed of small, icy bodies that orbit the sun beyond the orbit of Neptune. The age of a rocky body can be found by radioactive dating based on the decay half-life of radioactive atoms. The oldest rock from Earth, the Moon, and Mars have ages over 4 billion years. The oldest objects in our solar system are some meteorites that have ages of 4.6 billion years. That is taken to be the age of the solar system. Hypotheses for the origin of the solar system have been either catastrophic or evolutionary. Catastrophic hypotheses depend on a rare event such as the collision of the sun with another star. Evolutionary hypotheses propose that the planets form by gradual natural processes. The evidence now strongly favors the solar nebula theory and evolutionary scenario. Next lecture will be the terrestrial planets. And now I hope you enjoyed this lecture, and I am looking forward to see you soon. Bye.